Regression. Can you say in Russian way? Regressia, with a cool R. Regressia. Regression. Usually people use linear or not linear regression. Linear regression is the most popular one, but we're going to teach you more than that. So that is actually pretty cool that in this lecture, I noticed they want you to know quadratic regression, exponential models, logistics models, and so on. And I will show you a solution of your homework number 1, problem number 1, just to help you to figure out homework faster. So, regression can be linear, as you can see, linearly increasing. We give you dots. Dots are the data points. So you were observing birds in the island. I actually met with researchers at the conference. They dropped off on the island with a helicopter. Nobody can access this island unless you're a biology researcher. And then the student and the postdoc or a professor live there for a month or 2, putting cameras everywhere, exploring, tracking down the birds and how they put nests and eggs and relationship with predators. And then sometimes islands get flooded, so they have to go to the highest point, and they don't have any communication with outside world except one radio for emergency. And once it happened, it was such a strong storm, they had to call emergency helicopter, and that came and picked them up from the top of the mountain, and all the equipment got drowned, and they lost lots of equipment. So I met those people. It's very fascinating what they do. And this is what they do. They bring the data home. They bring the data points, how many nests were there at the beach, how many nests there were at the mountain location for the same types of birds, why they choose these different types of lives. And then something is increasing or something is decreasing. How would you know if you only see dots? You kind of play the child game when you try to approximate the dots. And that's what they call approximation, linear approximation or not. The first examples are linear, the other one is not linear. So, let's see. When you try to approximate dots with anything, any kind of function, for example, a line, you assume or even explain that there is an error there. And that is important to understand. As the researchers, we keep doing some errors. So this is the data point, but to be close to all of them at the same time, I'm drawing a line between them all to see the far-looking, the big picture. So all these researchers, they have error, and your job to make sure that error is not too big in total. Let's review what we did before and finally connect it to data science. So regression. Regression is going to be a method to estimate. A method to estimate. Today is just a party day. Today is a no bones day, so that's why. Yes, I am. Maybe that's why it's jumping. To estimate now when you said, now I'm not now. Okay. Yes, I am. Okay. The relationship between a dependent variable, var, that's variable, I like it. And let's call it y, and, well, y is capital Y, not necessary to make it capital, just your y. Y depends on x, so it's called dependent variable. And guess what? Independent variable. Independent variable. Let's call it x, but it can be anything. Time t, numbers of birds, b, numbers of grown-up birds, b, g. That's what usually we do, b sub g. Numbers of small birds, b, s, and so on. So, bless you. What kind of functions we learned? One of the most well-known around the world is a linear regression. So linear models were given to you not just to torture you. I heard some of you were asking during the class, why am I learning this? This is so boring. There has lots of applications. That's why there's a very good meme when there's like, I want to learn something practical. Teach us not the quadratic equations. Teach us, how to do investments and loan and calculating your student loans. Yeah, that's even harder math. So that's the thing. All of these actually have exponential growth, linear regressions, analysis of the quadratic functions. So actually it all depends on the models like linear functions, which are y equals mx plus b, and we learn how to create that. How do they look? They look like a line going up or going down. So the going up or going down, officially we call it increasing, decreasing. That depends on the slope, m. Usually, mathematics does not agree with statistics. We always make jokes that statistics is not mathematics. And they call it a in statistics. So let's call it a, but it's slope m, to be honest, but it's fine. If a is positive, the function is increasing. If a is negative, decreasing. So that's my slope. We know that. What other model did we learn after that? Or we just know? With Q, quadratic one. Quadratic model. Some behaviors have quadratic behavior. For example, any kind of thing I showed you funny in class, I'll remind you. Model this. Woo! What is that? A rock was thrown up, rocket was thrown out. How do you think they calculate in the army when they train people? At least in our country, in Ukraine, I know that if you are in army, they do give you math classes, statistical classes, to calculate if you shoot from the cannon, how would you reach the destination? It will go up, but at some point it will land the earth, right? It is a quadratic approximation there, and there are fast equations that you need to know how to use. Those are quadratic models. Y equals ax squared plus bx plus c. This one looks like the most famous one is going down and then up, a smiling one, concave up. Or going up and going down, that's throwing the marker up and it will land back. So goes to infinity, concave up, concave down, and we learn that the leading coefficient, again a, is positive to be concave up, so it's like a cup accumulating water, or negative for concave down, that is a mountain, so the water falls down. That's how I teach my classes, at least. And then we learn those fascinating ones, the fast ones. What's the name? Yes, exponential one, exactly. Exponential models. First, we learn unrealistic exponential models. Do you remember what I mean by that? When it's going up very, very fast and going down very, very fast forever. So always positive, never crosses the x-axis. And it has equation y equals a b to the x. So that is exponential growth, goes very fast up. If b is greater than 1, but if b is a fraction from 0 to 1, then this makes then it shrinks to 0, because fraction times fraction times fraction basically is dividing. Then it shrinks very fast, and at some point it shrinks to 0 but never reaches 0. So that is when b is from 0 to 1. When b is 1, it's just 1 times 1 times 1, it's a line. That's the base. The base b, that's what I call b. The base b here is important. So a was important for the quadratic, b is important for the exponential growth or decay.
Don't you draw what happens below 0?
We just know it. Exponential growth or decay. And we had several cool examples about that. But that was not a realistic model, because we all agreed. I showed you the mutation of the bacteria video, and just we were discussing, so I have a fish tank, and does it mean that the zebrafish will be exploding in forever into the population? No, they do have a limit, and that limit we called a logistic model. It's a model, still exponential growth, but with the restriction, logistic growth or decay model. Same thing, but now exponential function is growing. So let's say zebrafish, for example, is used in the labs so much, or mice, of course, too, but zebrafish actually gives you 55 babies every week. So you can check the tumor there. Cancer research is done on zebrafish. Poor zebrafish, just used everywhere. So it grows exponentially at first. But then at some point there's a restriction of the space, food, So just in general, resources get restricted. So it still keep growing, but now it has to take into account the restriction of the capacity. So carrying capacity, the limit of y. And that will be your realistic roof of the growth or decay. This formula is more realistic. It's still exponential growth, but it has a carrying double R, don't forget, carrying capacity. The limit of y as x approaches to infinity. So that's why we learned limits at the very beginning, if you remember, as x approaches infinity of y. Some kind of height. We can call it c. C. Height c. Gives you c. Capitals. Depends on the book, actually. So, what was the formula for that? And this is the formula none of you remember, I'm pretty sure. Because the formula was complicated. I even told you that I will not require you to memorize it, and I will give you on a test. C all over 1 plus a e to the minus bx. This was the formula. So depends on the b. It's kind of interesting to explain. In some books, b does not have a negative in front of it, so b can be negative or positive. So again, if b is negative, negative times negative is positive, that's one thing, and then b is positive, that will be negative, and so on. If you check the limit of this function of y as x becomes huge, then indeed the denominator gives you 1, because this function over here shrinks to 0 as x becomes huge. Check the property of exponential function, it shrinks to 0 over here as a decaying exponential function. So indeed it gives you c, and c is this limit when the function is keep growing. It has a restriction at plus infinity, is at this roof, which is c. That's called logistic growth model, and if it's going down, in logistic decay model. Before we go to the example, what do you think about that? Ask me. This is your homework example. I made a screenshot of it. But let me check. What do you think? Let me put some rainbow boxes. So, linear model, that looks to be the easiest one, and surprisingly, it's actually very practical. People use linear regression everywhere, and it has lots of cool ideas how to actually approximate. Quadratic models, I saw them, but not so much. Exponential models, not realistic, but logistic models. They are really good, and they are used quite a lot. Example of your homework example. Let's do it slowly, one by one. Picture 1. So I just made a list of these 4. Exponential, a times b to the x. Quadratic, ax plus bx plus c. Linear, mx plus b. Okay, it's definitely, the order is wrong, but it's fine. And logistic at the end. We did linear first. That's fine. So draw this one. So you collected the data, number 1. Data sample number 1. And for example, how many flies came, how many ants came to the candy you dropped on the floor? First there were lots of ants, and then slowly they were eating, taking away pieces, and it was going down and shrink to 0. Choose what kind of function it looks like from the list. What do you think? Exponential or logistic? What do you think? Because kind of logistics has a roof or a floor. How do you know which one is which? Logistics, I would say, growing and then has a floor, or decaying and then has a floor, so something like that. This one is not a floor, it's your right. It shrinks to 0. So if I want to play a kid's game when you connect the dots, you're not just connecting the dots like we were taught. You should try to connect the dots so that there were as small error as possible. Every time you are away from some kind of point, the error is big. So if you go too high, it will be very close to this point, but now it's far from this point. If you go too low, yeah, these 2 points got captured. This one is really good, but this one is too far, and this one is way too far. So there's some kind of perfect way to put a line where all those errors are minimized. Arrow should be minimized. That makes sense. You don't have to write it down. That definitely makes sense. You don't want to have a large error. So for this exponential function, I will take a pencil, and usually we tell our computers to do it. Computer know how to do it. And I will draw a nice looking going through most of them line. That does look like exponential decay. We don't have two formulas in the list for exponential growth or decay, but you remember exponential decay, we just reviewed, is when this b is negative. When b is negative, it's still the same formula, a b to the x. But since not negative, from 0 to 1, b is a fraction, then the exponential function shrinks. So it's a. And then in front of a, I'll put number 1, comma. Maybe we'll have more, just not put comma right away. How about the second one? Draw this data point, second one. Maybe this is the data you saw birds leaving the nest and coming back to the nest in the evening. In the morning, lots of them were leaving. In the evening, lots of them were coming back because it's time to protect the nest. You said it's quadratic. Let's try to see. It's going like this and going up. Looks like quadratic to me. Quadratic. Quadratic is B. So let's put it number 2. That's your homework problem. First one. B. All agree? What do you think? Now the third one. What do you think about the third one? Draw the data points. What do you think about this one? Looks like logistics, and it's growing logistically. So maybe it's a population of rats under your house in the sewer. It was growing super fast, but at some point there was less food and so on. So seems like it's a logistic model. And it's growing, by the way. So logistics model is sometimes decaying. Logistic model is growing. Let's find it in the list. This is the complicated formula over there, D. This is number 3, logistic model. 2 left. What about number 4?
4, that's linear.
Linear decaying or growing?
Decay.
Decaying. This looks like linear to me too. So linear. Linear was number 3 in this list. So it's C. This is problem number 4. And then there is one more. Draw this one. What do you think is that? Number 5. Exponential, but which one? Grows. Good job. So, you can be surprised why people paid 6 digits to do that. Because this is just the first step. When you can figure out this function, which is actually very hard, it's not visually easy like we're doing here. When you figure out the function, you can predict what happened next. And this prediction costs lots of money because this is a prediction of the oil prices. This is the prediction of statistical behavior of people. Oh, so they like Tide Pods now. Maybe we should put more Tide Pods in the front of the Walmart store. All of this, every Walmart, every store has a data scientist or statistician hired with 6 digits to predict this. Because they keep accumulating data from us. How often do we show up? What age shows up in the morning, midtime in the evening, what day of the week? And they move and relocate items based on that, especially holidays. And that's why math majors are so popular, because we get hired at every store or at any place. Hospitals need to know how much medicine to order for this month. If you order too much medicine, it will expire. If you order not enough, people might die. So this is also a prediction. You only have data on patients which looks like this. Using this prediction, you can know where it goes. So that is why it's so important, and people paid lots of money for that. Exponential growth, what number was it? A. So this one more is A, number 5. But now it is growth. Not too bad, what do you think? It's pretty fun, and I can see putting this on a test should be not too bad either. But after this, it gets harder, as you can imagine. Example number 2, lots of writing, so I'll give you some time. A rock is thrown upwards, its height in feet, t seconds after it is thrown, is recorded in the table. As always, nobody just show up in front of me and gave me the parabola function for whatever I just did. I threw the marker and you're like, sure, it's 5.0x squared minus 3x plus 10. How do we know that? So it's our job to build the function. Calculus teaches you how to work with functions, and finally you will learn how this function was built. And that is a pretty cool idea here. We need to know how to build those functions. So I don't give you a function. And to be honest, the function is given here as a table. There are three ways we can give you a function: as the graph, as a table, input versus output, and as the equation or relationship, y equals x squared plus 5, and so on. The data one usually is the hardest one because lots of points are missing. What happened in 0.1, 0.2, 0.3? We don't know. So we will have to connect the dots and figure it out. The points are at 0 it was 6, at 1 it was 90, at 2 it was 146, at 3 it was 165, at 4, and so on. It is a relationship between t and h, where t is the input and h is the output. Input, independent variable, and output, dependent variable. So now we have list of points, for example, 0, 6, 1 and 90, and so on. You need to learn how to plot this using graphing calculator or any other tool. I use Wolfram Alpha because I like it. You use graphing calculators because my country did not have graphing calculators when I was learning this. So I like using computers, Python, R, Wolfram Alpha, MATLAB, anything you can use is good. But since you guys all own graphing calculators because it's required, here it is. Here's the directions how to do it, so you can do it right now. How to plot the table of data points. I can show you this in Wolfram Alpha, and I gave you the link in my notes. You can check it out. It looks like so. Any computer can do it. Any computer program can do it. You just draw. You just put all those points in. And that's what I did. There was list of points. Oh, and I did not record it. Okay, that's mean. Oh, here it is. Okay. I just put all these list points here as a list of points. 0, 6, 190, 246, and so on. Click submit, and it gave me points. No line though. It gave me points. So in your case, you should do it like so. You click stat. Statistical calculators are amazing. They do lots of things for you very fast. It's basically little computers. Edit. Line 2 are your inputs. Line 1. Line 2 are your outputs. And then you plot it. Try and see if it works or not. There's lots of videos on this. So we made lots of videos for you. There are lots of people who are very professional in using graphing calculator in our school. So they made lots of videos on this. I will show you it here. Here it is. Lots of videos. These people, Heckman specifically, is really good in using graphing calculator, so definitely he did it a lot. And then you guys try it too. And see what it looks like. So it gives you some data points, some dots. Some dots. I would just do it by hand, but that's because I'm lame. You know, it's like old style kind of thing. But graphing calculators just do it for you. But I know how to draw 0 and 6 and 1 and 90. Why I have to overcomplicate this? I guess when you have thousands of data points, then yeah, that makes sense. And then for 1,000 data points, guess what you do? You have usually an Excel file, which you download and upload into the calculator or your program, and it will immediately distribute inputs and outputs and draw the curve for you. It will look like so. Let's see. For example, while you're playing with calculator, we'll show you fun stuff. It will look like so. Lots of points. That's a college GPA, scores for SAT math, and so on. Or it might look like so. So the more data points you have, you just upload an Excel file, and then the computer will figure it out for you. Or these, or just few of them. That's what we do right now. Or lots of them. Look at that. So it's pretty cool. There's lots of infinitely amount of possibilities you can imagine. And then the line tries to do the linear regression to approximate as many as possible. But in this class, we teach you more than that, not just the linear regression, which is the most popular, but others as well. So what did you get? Any shape we recognizing? looks like quadratic regression. So now you, she's giving you a recommendation here, the coordinator. So you're using graph, adjust the window to see all the points. Adjust the window probably from -1 to 6 to see more points. And from 0 to 200, not just 118. The bigger the window, the better the picture is. And then it will look like a parabola. It looks like a quadratic regression. Quadratic regression. Calculator knows how to deal with quadratic regressions, just like a typical program, Python and R+, and C++ and stuff, R. So you can actually go to stat, calc, plot, quadratic regression, apparently it's number 5, and it will connect the dots for you. Not just collecting the dots, it will give you the expression for the function that approximates those dots. And you expect it to be a parabola looking concave down, so the leading coefficient will be negative. And it's appeared to be this function. Let me zoom in for you. This function minus 15.5 and so on. So computer does this for you. Using, I'll keep writing, but you can keep typing. Using any tool, let's call it computer tool. Computer tool. We not only got the points, which looks like that. We're not going to use linear regression. Instead, we see, oh, that looks like a parabola. I use Wolfram Alpha because that's just easy for me. It looks like so. That's what I got. So you see this ending, it's my imagination. I can assume it will go down, but it's totally my imagination. But yeah, why not? Instead of doing linear regression, I can see it's quadratic regression. So apparently quadratic regression. Apparently programs can connect the dots for you and create a function. The function end up to be concave down, so we're expecting this, minus 15.5 x squared plus 99.5 x plus 6.4. So usually we are giving this function, and this is the first time I'm telling you that this is how you get to the function level. People are paid lots of money just to create this function out of data points. Because if you do data science, you don't have a function first. You have a data, and data is just a bunch of points, bunch of dots. So calculator computer can do it for you. It creates a function. And now you can find anything you want to do with this function. Global maximum, global minimum, increasing, decreasing, and so on. Concave up, concave down. But this is the most important part. This is where the data science happens, where statistics is happening. And now you can do statistical analysis. In this case, it's just calculus. That's what you call calculus. A, create a scattered plot in calculator. We did it. Find a function that models the height. We did it. Estimate the rock's maximum height. Okay, that's C. Maximum height. They just want to estimate. Two ways of thinking about that. This is the parabola concave down. The maximum height is somewhere close to the vertex. Vertex has a formula. Either you use this idea that vertex has a formula y equals minus b over 2a, where this is my a, it's negative, this is my b, and this is my c. Vertex is always a global maximum or global minimum for the parabola. Or we can use finally our derivatives. If I differentiate and set something equal to 0, then it will give me maximums or minimums, if you remember. So maybe let's do that, because it's just kind of also fast and fun. Y prime is minus 15.5 times 2x plus 99.5. That is my derivative. Set it equal to 0 and solve for x. X is, also it's not x, it should be t, if you remember. That is, if we want to be consistent with the book, we should rename it to t. Says rename it t seconds. it is t and t here, and then also t over here. So when the rock reaches its maximum, when I solve this equation, which is 99.5 over minus 2 times 15.5, which is approximately 3.2 seconds. In 3.2 seconds, the rock reaches its maximum, or the cannon, if you're shooting the cannon, when it's going to reach the maximum, in 3.2 seconds, or whatever you're throwing. How do we know it's a maximum? Remember, parabola concave down. Here, your derivative y is 0. So we can just solve when this happens. Apparently, for t, this happens approximately at 3.2. Do you see any connection between the first method and the second method? What do you see? Kind of curious. Yeah, it's the same thing. Minus b is exactly minus 99.5 over 2a. So it's minus, oh, did I lose the minus? Yeah, no minus here, that's one. Well, it's minus. Double minus gives you plus. Minus 2 times a, 15.5. So it's the same thing, and that's not a mystery. That's how it was created. Vertex was found from differentiation, from finding maximum or minimum. What do you think about this? Very unusual, but it's exactly what we all were getting. 2 applications of calculus in real life. This is regression topic. Ask me, I will stop for a second. Or keep writing. What do you think? Yes?
How did you get the equation, I guess, in the calculator?
Oh, how to get in calculator?
Yeah.
So she says you do it this way. Somehow it should magically show up. Apparently it's a button number 5 in Stat, Calc, and 5.
Cool.
And that's why they made several videos about this, showing you with hands how they do it. I just don't like doing it. But there's so many videos done how they show you with hands, how they click. Also, you can also Google YouTube's lots of people making money on you watching the YouTube videos, how they click and calculate. So I did not feel like I want to do one more video like that. More questions? Then one more problem. That's also kind of a homework problem. Approximate the population using a regression model. Again, with the population, you don't have a formula. You have just data points. At the year number 1, it was 2,000, say, people. Year number 2, 3,000, and 5,000, 8,000, or rabbits, or birds, or whatever we want, and so on. 2 questions. Use the model to approximate something in the future. And that makes sense. It's exactly why we want to do that. We want to approximate how many patients there will be next month in order to order more medicine. Or how many wheelchairs we will need. How many rooms do we need next month? Taking into account the flu season, taking into account it's not the flu season, and so on. Or sometimes you have a perfect approximation, and then some kind of huge accident happens on the Highway 80. And now we need all those beds taken away, but the flu season is still ongoing. So all of this is done using math and statistics. Do you want to figure out what happens at 8? Or after t equals 8? Moreover, they also want to know how fast that is a derivative. Remember, how fast means derivative is the population growing at 8. So after t, that's just a function at 8. How fast at t, that's a derivative at 8. We want to know the slope. Like, is it keep growing? Is it keep decaying? And so on. Use the graphing calculator. Create a point. You increase the window. Let me do it like so. Use the same function in the calculator you had before. 0, 6, 1. Increase the window to see more points. 1,000, 1,500, and 1,000. And let's see what you're gonna get. You're supposed to see something. The thing is, we already learned that population modeling has exponential growth or decay, right? And they already gave me the way that it's growing. How do I know? From data points. I look at this and like, okay, whatever it is growing, whatever is the data point, it was 2,000, 3,000, 5,000, so it is growing. And we do know that population growth is usually exponential growth. So we can just use this knowledge to figure out that probably it will be the formula number 3. We already had quadratic model. This probably will be exponential model or the logistic one. So let's assume it's exponential model because we don't know what the roof is. We don't have enough data points. Y equals ABX to the x. When you sketch those points, y equals AB to the x, isn't it exponential growth, population model, and if it's decay model, then B is just a fraction, so we know that as well. Again, you can use any tool to plot the points, and to be honest, as the person who just looks at the table, say for the second time in my life, I see at 1 it is over here 2,000, at 2 it is over here 3,000, at 5, at 3 it's 5,000, at 4 it's higher, and at 5 it becomes even higher. Well, yeah, it kind of looks like exponential growth. So to be honest, even without calculator, you can kind of figure it out. It's only 5 points. If you have 1,000 of them, yes, that is hard to plot. But this is how it looks like. Exponential growth population model. So we don't know anything. We don't know A, B. What should we do? That's why we use a calculator. In the calculator, there is a function. Go to stat again, stat, go to calc, and apparently the button will be now 0. Because it's so popular, it's there, it's the first one. Exponential regression. And it will give you a function. Bless you, it will give you a function y equals, and it will figure out what is the initial point when x is 0. 1, 2, 3, 4, 5. What happens at 0? What is the growth rate B, and so on. So we do expect the initial point to be positive because we're talking about population growth. Something should be there first to grow. And then we do expect the thing inside to be greater than 1 because if it's from 0 to 1, it will decay. And indeed, the calculator gives you 1.59. This is your B, and B is greater than 1 in order to have exponential growth. Growth is when B is greater than 1. And this is A. So calculator or computer does it for you. And I will put this in the box. That's basically the most important part is here, because after this you just perform the analysis using calculus or calculator or Googling any friend. This is what people are paid for, are to perform this calculus analysis on this function. So this was question number A. A actually immediately asks, use this formula to approximate what happens when t is 8. Okay, when t is 8, that's what we did in your homework last month. It will be, also did they tell us the name of the function? No, not really. So you can call it any letter you want. We can keep it y or f or p. So it would be smart to call it p of x. Population usually is called p. But technically speaking, you can use the first letter of your name if you want. Doesn't matter. P at 8 will be plug in, and it's approximately 50,027.8 units. So whatever it is, birds and or whatever. Makes sense. So we asked what will be the next step. We wanted to guess the next point from 5 to 8. It was 12,500, and now look how it jumped. Since it was pretty far over here at 8, it also jumped pretty far. So the jump is so far that indicates exponential growth. See? It makes sense. Exponential function is growing fast. But then B asks how fast. Question, how fast means differentiation. So let's perform differentiation and we're done. P prime in general first is copy the constant 1230.84 times. Copy the exponential function to the x, because e to the x gives you e to the x when you integrate or differentiate. But what is extra here? It's not e? ln of what? 1.59. Thank you, ln of 1.59. Remember, a to the x prime is you copy times ln of the base. Thank you, good job. I was wondering if any still remember this. Fixing the situation that the base is not e is a natural number, so usually it's in the nature happens that you have e. But in general, as you can see, it's 1.59. E is like 2.7 something something. We got this part, so now we can plug it in p prime at 8. Plug into your derivative, and it gives you 2, 3, 1, 6. 1, 6 or 5, 6. What do you think that means?
That's how much you grew by every one.
By 1 unit. In this case, they told us it's years. Exactly, thank you. It says T are in years, so it says per year. So not only we know the number at 8, but we also know that the slope there is positive, so it's keep increasing. Well, it makes sense, exponential function. And we know by how much it will increase. So if this is the population of cows in the whole island, you can see that it will explode in so many cows that maybe you need to create some kind of restrictions there, so cows will still have enough land and food to eat. So this is the rate per year. That's kind of all. So we will start exam review, and we will have exam on Monday. Same location, 12:10 p.m. Yes?